Bismillahirrahmanirrahim. Assalamu alaikum. Moving forward, we will be now discussing Cauchy Goursat theorem for multiply connected domain. For multiply connected domain. Multiply connected domains. So in particular, we will be first talking about doubly connected. Doubly connected means a domain with one hole. Doubly connected domain. And if I say more specifically, then we will discuss basically the principle of deformation. The principle of deformation. Principle of deformation. Okay. Consider first doubly connected domain. Doubly connected domain means a domain with one hole. So as shown in the figure that we have considered a domain having one hole, and we have also uh, drawn two contours. One is C, which is over here, positively oriented, and the other one is the C1, which is having this kind of uh, clockwise orientation. So this is doubly connected domain. Doubly connected means it is in a special case of multi-connected domain, right? What can we do? Basically, we can define a cross cut. So like we can make a cut over here, and with the help of this cut, so you can imagine that you have something like this. So like now your domain is something like this. So you have made a cut over here and separated in this way. So this cut over here can be labeled as like, if I say point A here, so this is point B here, so this is AB, and this is going to be if this orientation is this way, then this orientation is going to be this way. So now this particular so the meta conclusion is now this domain becomes simply connected, right? So you can if you find any simple closed contour which is entirely sitting inside, then you can uh, shrink it to a point without leaving this D, right? But in over here you can't do that. So what I can do now, suppose I have got a f of z function and I want to integrate it over this. So what I can do basically, so there are basically four curves. So one is C over the C. This is C. So like I can define a quantity which is equal to 0. There are basically sum of four quantities which is going to be equal to 0, and one is the contour integral of f over this C, which is the this one over here C, and then plus AB integral of f of z over AB plus integral of minus AB over minus AB of f of z dz plus integral over C1 of f of z dz. This has to be equal to 0, because you basically are covering a closed path, in other words closed contour. So from here this will get to 0 using the property, and from here what can I conclude? The integral over C of f of z dz should be equal to minus times, but because the orientations are opposite, so like I can write uh, in the positive sense. So this something, this equality of the integrals is known as the principle of deformation. So it says that if you have a doubly connected domain with one hole, so let's say we have a doubly connected domain, so there is a hole, let's say this is a hole. Now over this hole, if you have a C1 as a curve and another one C2 as a curve and another simple closed curve, and let's say there is another one as well, C3, which is also simple closed curve. So over all of these, your integral is going to be same. So you can say that over all of these, curves which are, surrounding this hole, so over C1, the integral is same as over C2, is same as over C3. So what is the benefit of this? The benefit of this comes in the form of, simplifying the integral. So like if I have got a doubly connected domain and there is a hole, and over this hole I have a curve, and I wish to compute integral over this curve, but I have got a kind of relaxation that I can make an other curve which is easier, over which there is easiness to compute the integral, so I can use that. So if I have a domain and there is a hole, and over this hole, over that hole there is a curve, and I want to compute integral over this simple closed contour, then I can also use an other contour which can be easier or convenient than this, and I can compute over that because this is going to be same as over this. I hope that makes sense. So I will solve this integral. The integral is over a simple closed, over a closed contour C of the integral of the integrand function, which is 1 over z minus I dz. So we want to solve this integral, and the domain or the C is given by, where C is the curve as shown in the black. So this one is the curve basically. Which is basically combination of different lines. So it is closed. We want to integrate this function 1 over z minus iota over this contour, right? If you notice, or if I ask the question, can I apply Cauchy Goursat theorem and say that this is equal to 0? The answer is no, because we have got non-analyticity, or the function is not analytic as at a point. So my function is f of z equal to 1 over z minus iota, and in order to see such type of functions, we basically set the denominator to be equal to 0, and from where we see that z is iota. So in other words, when z is iota, our function is not analytic. So this means that if I consider this, the version of the Cauchy Goursat theorem, it was saying that if a contour, if a function is analytic within and on the contour, then its integral becomes 0. But if that is not the case, or in other words, if a function has got non-analyticity inside or on the closed contour, then we can't apply Cauchy Goursat theorem directly, but we can apply deformation principle. And the deformation principle says that, so the meta conclusion of the deformation principle was that if there is a hole, and over a hole in the domain, and or a hole inside a contour C, let's say, and we want to integrate a function f of z over this contour, let's say this is C1, which is a closed curve, then you can also consider another C2 conveniently, such that integral on the C2 and C1 remains the same. So because the function is non-analytic at this point, so in other words, I can treat that this is a kind of hole. So instead of integrating this function over this contour, which is now shown in the green, I can consider another closed curve, which is a circle centered at iota, uh, whose equation in parametric form can be given by z of t to be equal to iota plus center, let's say radius is 1, so 1 e to the iota t. So this is going to be the equation of circle of radius 1 centered at iota, right? So I can consider this contour now, and I can integrate this integral, and the result will be same as that of integrating over this this contour which is given in the green. So let's apply the formula, and formula says that when you integrate this function over a contour, then you can write a to b f of z of t times z prime of t dt. Of course, in this case, t runs between 0 and 2 pi. So all I need to compute is f of z of t and z prime of t, and my a is 0 and b is 2 pi. So I can apply this formula and calculate the integral. So because my f of z is equal to 1 over z minus iota, so f of z of t will become 1 over iota plus e to the iota t minus iota, which is basically e to the minus iota t, and z of t is equal to iota plus e to the iota t. So when I differentiate this guy, I'll get iota times e to the iota t. Now I can substitute these values and integrate f over c, which turns out to be equal to 0 to 2 pi f of z of t, which is basically 1 over e to the iota t, or e to the minus iota t, it is same, and the derivative of z is e to the iota t dt. Now this gets cancelled with this, and it turns out that it is equal to 0 to 2 pi I dt, or this is equal to 2 pi I, right? So this is the integral. I have taken a circle of radius 1. You could take another circle of radius, let's say 2, and perform the same, computation, and it will turn out that it is also equal to uh, 2 pi I. One can take even a radius equal to r. Let's say I can take another circle of radius, say r. So r can be anything, 1, 2, 3, centered over iota. Then I can compute. So my parametric equation will be z of t is equal to iota plus r e to the iota t. So its derivative is equal to r I e to the iota t, and my f of z of t in this case is going to be 1 over I plus r e to the iota t minus I, which is equal to basically 1 over r times e to the minus iota t. Now we can apply the formula of integral of f of z over this contour to be equal to from 0 to 2 pi f of z of t, which is 1 over r times e to the minus iota t times z prime, which is r times iota times e to the iota t dt, and this gets cancelled with this, so you have same 2 pi I. So you can take any kind of circle of radius, so radius 1, 2, 3. So it turns out that this is the same. One nice other example that we can solve, but in the next video.